Hello students, today we are going to discuss one important distribution, that is Poisson distribution, which comes under discrete distribution. So, the objectives of Poisson distribution is, after studying this unit, you will able to identify the situation in which Poisson distribution can be used. Define its probability mass function. Understand the characteristic properties of Poisson distribution. Obtain various statistical measures associated with this distribution. Understand the additive property of this distribution. These are the objectives of this particular distribution. We are going to discuss introduction of binomial, like earlier we discussed binomial, Poisson and Bernoulli distributions. These are comes under discrete type of distributions. Now, who is introducing this particular Poisson distribution? A famous French mathematician, his name is Simon Denis Poisson, introduced and proposed this distribution in the year 1837. This is the another theoretical distribution that has wide applications. When the probability of occurrence of an event is very small, but the area of opportunity is very large, this distribution can be used. This distribution can be used. When we can use this distribution, the event is very small, but area of opportunity is very large. In that case, this Poisson distribution can be used. Some of the situations in which this distribution can be used are: the number of cars crossing a junction in a fraction of a second, the number of deaths due to a rare disease, the number of emissions from a radioactive substance in a given unit of time, number of printing mistakes in a textbook. Have you understand these all the four examples? First one is number of cars crossing a junction, number of deaths due to a rare disease, number of emissions from radioactive substance, number of printing mistakes in a textbooks. All these comes under small number of events, but range is wide. In this situation, we can apply Poisson distribution only. So, definition of Poisson distribution: a discrete random variable x is said to have the Poisson distribution with parameter lambda if it assumes only non-negative integer values and its probability mass function is given by probability of x is equal to small x is equal to p of x is equal to e to the power of minus lambda into lambda power x divided by x factorial, where lambda greater than 0, x takes a values 0, 1, 2, 3 and so on. Otherwise, the probability mass function p of x is equal to 0. Then I can say this probability mass function of the Poisson distribution is e to the power of minus lambda, lambda power x divided by x factorial, which is the probability mass function of the Poisson distribution. Poisson distribution can be obtained as a limiting case of binomial distribution under the following conditions. Okay. So, Poisson distribution can be obtained as a limiting case of which distribution? Poisson distribution can be obtained as a limiting case of binomial distribution under the following conditions. Which conditions? Under which condition this distribution follows limiting case? So, that means the number of independent trials n is infinitely large. In binomial distribution n is finite, but while coming to in this binomial Poisson distribution n tends to infinity. That is first condition, the number of independent trials is n, which is infinitely large, that is as n tends to infinity. The probability of success P is very small, that is P is almost P tends to 0, just like previous examples. Number of roads cross in a junction, number of printing mistakes in a textbooks, those are very small events. Under that case, P goes to very smaller value. And NP is what? Mean of the binomial distribution, that NP is equal to lambda is a Poisson constant. Under the above these three conditions, Poisson distribution can be obtained as a limiting case of binomial distribution under the following conditions. Now, we are going to discuss properties of Poisson distribution. Properties of Poisson distribution. When X has a Poisson distribution with parameter lambda, let us denoted by X follows P of lambda. X follows P of lambda. Lambda is what? Lambda is a parameter. So, mean and variance of Poisson distribution. How to find the mean and variance of the Poisson distribution? By making use of probability mass function of Poisson distribution. If X follows P of lambda, then the first moment about origin is mu n dash is equal to, we know that in terms of mathematical expectation, that is expectation of X. Expectation of X is nothing but what? That is the mean of the corresponding distribution. So, expectation of X is equal to summing over X takes a values where to where? According to our probability mass function, X takes a values 0 to infinity, X into P of X, where P of X is what? P of X is the probability mass function of Poisson distribution. So, now we can substitute instead of P of X here, summing over X is equal to 0 to infinity, X into e to the power of minus lambda, lambda power X divided by X factorial. So, lambda is a constant, e power minus lambda is a constant taking outside of our summation, because X takes a values 1 to. Now, we can decreasing the terms, X is equal to 1 to infinity, X into lambda to the power of X minus 1 divided by X minus 1 factorial. X term we can decreasing one term and lambda power X we can write here. So, lambda power X minus 1, then 1 divide and multiply with 1 lambda, then it becomes, we can take outside of that function, that is lambda into e to the power of minus lambda. So, now we can expand this summation, we will expand it, then mu n dash is equal to lambda. Therefore, mean of the Poisson distribution is equal to lambda only. Now, we can go for second order moment about origin is, why? Because we would like to find the variance of the Poisson distribution. How to find the variance of the Poisson distribution? So, variance of the distribution, variance of the Poisson distribution is equal to, which is represented by variance of V of X. V of X is equal to expectation of X square minus expectation of X whole square. Now, already we got mean of the distribution, mean of the Poisson distribution, that is lambda. Now, we would like to find the mu 2 dash is equal to expectation of X square. Expectation of X square is equal to summing over X is equal to 0 to infinity, X square into P of X, where P of X is a probability mass function, where P of X is a probability mass function. Then this X square we can write X of X minus 1 plus X. If you can simplify this, we will get X square, because I would like to expand this summation, that is why I can write X square term I can represent in terms of X of X minus 1 plus X into P of X. Here if you can expand this summation, we will get two terms, X of X minus 1 into e to the power of minus lambda, lambda power X by X factorial, plus summing over X is equal 0 to infinity X into P of X. So, this is already just now we got this value, that is mean of the Poisson distribution, that is lambda. Again we can simplify these terms, those terms are, again we have to simplify, and after simplifying we will get that variance of the distribution. That is, variance of the distribution is equal to what? Mu 2 dash minus mu 2 dash minus mu 1 dash whole square. So, that is lambda. Therefore, in all the distribution function, only one distribution is having mean and variance both are equal. Which distribution is? Only Poisson distribution. So, I have to dear students, just to remind this thing, only this is a very important case. So, only one distribution is having mean and variance both are equal, which distribution is known as Poisson distribution only. So, mean is equal to variance is the characteristic feature of the Poisson distribution, that is a distinguished feature of the Poisson distribution compared to other distributions. Now, coefficient of skewness and kurtosis. So, what is the skewness and kurtosis of this Poisson distribution? If x follows P of lambda, then the coefficient of skewness is beta 1 is equal to, we know the formula, beta 1 is equal to mu 3 square divided by mu 2 cube, mu 2 cube. So, already you know mu 3 whole square, that means mu 3 is equal to lambda whole to the power of 2 divided by lambda cube is equal to 1 by lambda. So, therefore, beta 1 is equal to 1 by lambda. Beta 1 is equal to what? Beta 1 is equal to 1 by lambda. So, gamma, how to get the gamma? Gamma 1 is equal to under root of beta 1. We know that gamma 1 is equal to under root of beta 1. So, now already you know beta 1 value. What is the beta 1 value? 1 by lambda. If you can substitute this instead of beta 1, that becomes 1 by under root of lambda. So, now we can remember one important note from this, we can identify, we can remember this point from this note. Poisson distribution is always asymmetric. Poisson distribution is always asymmetric. Why? Because beta 2 is equal to what is the beta 2 formula? Beta 2 is equal to mu 4 by mu 2 whole square. That is, after simplifying mu 4, already you know that. What is the mu 4 value? 3 lambda square plus lambda divided by lambda square. Therefore, after simplifying this, 3 lambda square by lambda square plus lambda by lambda square. So, lambda square will be cancelled. Here 1 lambda will be cancelled in second term. Therefore, this we can write in terms of beta 2 is equal to 3 plus 1 by lambda. That is also we can write in terms of relation in terms of gamma 2. Gamma 2 is equal to beta 2 minus 3. Gamma 2 is equal to beta 2 minus 3. So, therefore, now we can say what is the beta 1 value? Beta 1 is equal to 1 by lambda. Gamma 1 is equal to 1 by under root of 1 by lambda. Beta 2 is equal to 3 plus 1 by lambda, and gamma 2 is equal to beta 2 minus 3, that is equal to 1 by lambda. Now, we can say, now we can conclude beta 1 is equal to gamma 2 na, both are equal. When lambda tends to infinity, beta 1 goes to 0 and beta 2 goes to 3. In that case, this Poisson distribution tends to a normal distribution. That is why we can say beta 1 is goes to 0 and beta 2 is goes to 3, as when we will get these two values as lambda tends to infinity. Then beta 1 tends to 0 and beta 2 tends to 3. In that case, Poisson distribution tends to a normal distribution. This is the foremost important distribution. In future, you can study this, studied about this normal distribution also. Now, we are discussing few important functions of the moment functions of the Poisson distribution, like moment generating function and characteristic function. So, first of all, we are going to discuss moment generating function. What is the moment generating function of Poisson distribution? If x follows P of lambda, then its moment generating function is. So, moment generating function simply we can represent it by mx of t. Mx of t is equal to expectation of e to the power of tx. In terms of summation, if you can take x takes a values where to where 0 to infinity. e power tx into p of x, where p of x is what? Where p of x is a probability mass function of which distribution? Poisson distribution. So, what is the probability mass function of Poisson distribution? E to the power of minus lambda power x divided by x factorial. We can substitute these values, that means here e power minus lambda power x by x factorial. Here e power minus lambda is a constant taking outside of our summation. So, summation is not applicable for e to the power of minus lambda, that is why we are taking outside of this e power minus lambda. X is equal to 0 to infinity lambda into e to the power of t whole to the power of x. We can treat lambda into e power t is considered as a one single term, okay, whole to the power of x we have divided by x factorial. Now, we can expand this summation. If we can expand this summation, this becomes what? E power minus lambda into e to the power of lambda into e to the power of t. That means, here e to the power of bases are equal, power should be added. You can apply that things. Now, lambda is a constant, e to the power of minus lambda is a taking outside. In that case, we will get mxt is equal to e to the power of minus lambda of 1 minus e power t, 1 minus e power t. So, which is the moment generating function of Poisson distribution. Therefore, so moment generating function of Poisson distribution is e power minus lambda into 1 minus e power t, which is the required moment generating function of Poisson distribution. We know that mu 1 dash is equal to lambda, mu 2 dash is equal to lambda square plus lambda, mu 2 is equal to mu 2 dash minus mu 1 dash whole to the power of 2. If you can simplify this, you can substitute mu 1 is equal to lambda here, then mu 2 dash is equal to lambda square plus lambda. So, we can substitute these values in this mu 2 formula. Therefore, mu 2 is equal to lambda square plus lambda minus lambda square. This lambda square minus lambda square will be cancelled, only remaining term is lambda. Therefore, mu 2 is equal to lambda. So, now once again you can tell me what is the value of mu 1 dash? Mu 1 dash is lambda, mu 2 dash is equal to lambda square plus lambda, then mu 2 is equal to lambda. So, mu 1 dash is known as a mean of the Poisson distribution, mu 2 is represented as a variance of the Poisson distribution. So, mu 1 dash is equal to lambda and mu 2 dash is equal to lambda. So, therefore, we can say that, so mean and variance of the Poisson distribution are equal. In similar manner, we can obtain mu 3 dash as mu 3 dash is equal to lambda cube plus 3 lambda square plus lambda, and mu 4 dash is equal to lambda power 4 plus 6 lambda cube plus 7 lambda square plus lambda. Using them, we can find out mu 3, mu 4 and then find beta 1 and beta 2, beta 1 and beta 2. So, now next important property of Poisson distribution is cumulant generating function. Like earlier, just now we discussed moment generating function of Poisson distribution. Now, similar manner we can go for cumulant generating function. So, this is very important and easy to generate this function, because so while compared to previous one we can apply some differentiation and put t is equal to 0, and then we will get different orders of the distribution. While using this cumulant generating function, so what is the cumulant generating function of Poisson distribution? If x follows p of lambda, then its cumulant generating function is, so cumulant generating function is represented by kx of t is equal to mx of t, that means log of e to the power of minus lambda of 1 minus e power t. What is this? Log of moment generating function of the Poisson distribution. So, how we will get the cumulant generating function? Cumulant generating function is equal to log of mxt, where mxt is what? Moment generating function of Poisson distribution. Just now we derived mxt. What is mxt value? E to the power of minus lambda of 1 minus e power t. We know that e power of f of xt, log of e to the power of f of xt is equal to what? F of t. This function we can write log of e to the power of f of xt, that is a standard formula, that is equal to f of x. What is f of x here? Minus lambda of 1 minus e power t, 1 minus e power t, that is we can write, simplify this expansion, then we can write lambda of 1 plus t square plus 2 factorial plus and so on minus 1. So, lambda of t plus t square by 2 factorial plus t cube by 3 factorial and so on, simplify like this, then we will get mu 1 dash is equal to lambda, mu 2 dash lambda square plus lambda, mu 3 dash lambda cube plus 3 lambda square plus lambda, mu 4 dash is equal to lambda power 4 plus 6 lambda cube plus 7 lambda square plus lambda. Though we can find out the central moments and beta 1, beta 2 coefficients. Okay. Using this relation again, like we can find out mu 1 dash, mu 2 dash and mu 3 dash, mu 4 dash. Mu 1 dash is equal to lambda, mu 2 dash is equal to lambda square plus 4, mu 3 dash is equal to lambda cube plus 3 lambda square plus lambda, mu 4 dash is equal to lambda power 4 plus 6 lambda cube plus 7 lambda square plus lambda. Okay. These are the relations. We use this relation we can find out the beta 1 and beta 2 values. Now, additive property of Poisson distribution. This is important distribution in Poisson distribution. This is a very important property, which property is known as additive property of Poisson distribution. Suppose x follows p of lambda 1, comma y follows p of lambda 2 are independent Poisson variates, So, z is equal to x plus y. So, then we can write pi of z is equal to pi of z of t is equal to pi of x plus y of t is equal to pi of x into pi of y, since x and y are independent. Then we write e to the power of minus lambda 1 of 1 minus e power I t into e to the power of lambda 2 of 1 minus I t. These are the characteristic functions of Poisson distribution. Then you can simplify numerator terms, bases are equal, power should be added. Here we can change these two symbols, right? You can write e to the power of minus of lambda 1 plus lambda 2 of 1 minus I t, which is the characteristic function of Poisson distribution with the parameter lambda 1 plus lambda 2. From this we can observe that the difference of two independent Poisson variates is not a Poisson variate. The difference of two independent Poisson variate is not a Poisson variate. Which one is satisfy this condition? Only sum of the two independent Poisson variates is a Poisson variate, but the difference of two independent Poisson variates is not a Poisson variate. This is a very important condition, important additive property of Poisson distribution. Now, we are going to discuss one more important relation of the Poisson distribution, which is known as a recurrence relation of the Poisson. So, what is the use of recurrence relations? Using this recurrence relation, we can find the fitting of a Poisson distribution. What is the use of fitting of a Poisson distribution? We can estimate the expected values and observed values and expected values, forecasting the difference between these two. So, what is the recurrence relation of the Poisson distribution? Okay. Now, I am going to discuss recurrence relation of for Poisson probability is, if x follows p of lambda, then P of x is equal to e to the power of minus lambda, lambda for x divided by x factorial, where lambda greater than 0, x takes a values 0, 1, 2, 3 and so on. P of x plus 1. Now, first one is P of x term, then I can take P of x plus 1 term. So, P of x plus term 1 means what? Whenever the x is there, instead of x I can substitute x plus 1. That means e to the power of minus lambda into lambda whole to the power of x plus 1 divided by x plus 1 factorial. Now, I can take P of x1, P of x plus 1 divided by P of x. Take a ratio between these two, that is equal to lambda by x plus 1. Then I can write P of x plus 1 is equal to, P of x plus 1 is equal to what? This P is coming to this side, therefore, we can write P of x plus 1 is equal to lambda by x plus 1 into P of x. X takes a values 0, 1, 2 and so on, and with the probability of 0 is equal to e to the power of minus lambda is the recurrence relation for Poisson probabilities. Is the recurrence relation for Poisson probabilities. Now, one more important property of Poisson distribution is mode of Poisson distribution. What is the mode? Most frequently value in the distribution is known as a mode. What is the mode of a Poisson distribution? How to find a mode of a Poisson distribution? So, we can establish one relation. By making use of these conditions, we should identify the mode of a Poisson distribution. That is, when x follows P of lambda, where P of lambda is what? Probability mass function of the Poisson distribution. What is the probability mass function of the Poisson distribution? P of lambda is equal to e to the power of minus lambda, lambda power x by x factorial, as you know this, where when lambda is a positive integer, then m. So, when lambda is a positive integer m, then we have mode at x is equal to m minus 1 and x is equal to m. That means, mode is gives two values. When lambda is a positive integer, mode is equal to, we will get two modes. One is x is equal to m minus 1 and x is equal to m, x is equal to m. These are the modes. If lambda is equal to m plus f, where m is a positive integer, f is lies between 0 and 1. In this case, the distribution is having unique mode at x is equal to m, at x is equal to m. So, now how to identify the mode of the distribution? There is a two cases. Lambda become a positive integer. If lambda is a positive integer, we are getting the mode is equal to x is equal to, mode is represented by x is equal to m minus 1 and x is equal to m. If m is lambda is not a positive integer, then your lambda is equal to m plus f, where m is a positive integer, f is lies between. In that case, mode is in this case distribution is having unique mode at x is equal to m. Now, we can conclude this our session. The summary of this today's lesson is, who is introducing this Poisson distribution? As you know, Simon-Dennis Poisson proposed a Poisson distribution. It is also called the distribution of rare events. The distribution of rare events. There is only one parameter involved in this distribution, which distribution is known as a Poisson distribution. Why? Because every distribution is having one or two parameters, two or more parameters, but especially in this distribution we have only one parameter, that is lambda only. For a Poisson distribution, mean and variance is equal to lambda, where lambda is a parameter. So, this distribution is having the characteristic feature of Poisson distribution, because only one distribution is having mean and variance, both are equal. Both are equal. For a Poisson distribution with parameter lambda, beta 1 is equal to 1 by lambda, beta 2 is equal to 3 plus 1 by lambda. The moment generating function of Poisson distribution mx t is equal to e power minus lambda of 1 minus e power t. the characteristic function of pi of x t is equal to e to the power of minus lambda of 1 minus e power I t. I hope everyone is understanding this class. So, any queries, any questions, you may be contact at the rate of given mail ID. We will discuss any queries, any questions. So, your doubts clarified through that through mail. Thank you all.